So in estimating mu, it's not enough just to use a point estimate that is one point, one value. So typically what we do is we surround our best guess with a little margin for error. So we'll take x bar minus e to x bar plus e. So e is our margin of error. Now, how do you calculate that margin of error? Well, it's actually kind of a little involved. And the formula for that is E is going to equal T sub alpha over 2 for the appropriate degrees of freedom times S over the square root of n. Wow. That's actually quite a mouthful there. Now, the one thing that I want to point out, though, is that one of the things that we're going to need is this. It's a T value, and it's a new distribution. Now, the distribution that we're used to is the normal distribution, but the student T distribution is going to be different than that. And I sent you out a link on that, but let me talk a little bit about the history of the student T distribution, because I happen to like this guy a little bit. William Gossett Jr. worked for the Guinness Brewery back in the 1800s and early 1900s, and he developed the student T distribution, and he was kind of humble, and so he named it after you, students. And this is a little plaque here that's in Dublin someplace in honor of him. And it shows you a little bit, it seems to me, I probably should zoom in on this, but it seems to me that it shows you one of the important features of the student T distribution that you can see when you look at this little graph here. So this is the Desmos link that I sent you on the normal and T distribution. And let's learn a few things about the T distribution. We'll call it our list of top facts. So student T distribution. Top facts. So some of the things we can look at the T distribution and kind of figure out for ourselves, and some I'm going to help you out with. But let's start by looking at the shape of this. Now, if you're looking at the T distribution, yeah, I'm hoping that maybe this is dialed down a little bit. Yeah, maybe n equals 2 here. If you scroll up and down on the Desmos link that I sent you, the red curve is the normal curve. The blue curve is the T distribution. You can see they're similar in shape. One is a little bit more spread out than the other one. That would be your student T distribution. And one thing that's similar, though, there's actually a couple things that are similar. We'll start out with the mean of this distribution. What do you think the mean of the student T distribution is? The mean of the blue one? 0. Has the same mean as the normal distribution. So the mean equals 0. Or I could write mu equals 0. Cool. Another thing to notice about the student T distribution is that it's symmetric. So the left and right hand sides are mirror images of each other. Now there is something that's decidedly different about the student T distribution as opposed to the normal distribution. And that is, it's going to change with degrees of freedom. And what on earth are degrees of freedom? Well, I'm going to abbreviate that DF from here on out. But let me show you an example to try and help you understand what degrees of freedom are in kind of a vague sense, but give you a little bit of practice with it. Suppose I have 4 students that I'm going to put in order. Now, we know that I have 4 choices for the first one, 3 choices for the second one, 2 choices for the third one, and 1 for the last one. So we're familiar with this. That's 4 factorial. That's fine. It's 24. But if you look at the number of choices that I actually had, I could choose who sat here, here, and here. But after I finished assigning the first 3, did I have a choice as to who got this last seat? No, right? You had choices for here, here, and here, but when you got down to this last seat, then you were stuck. It's like, okay, whoever's left, that's who's sitting in that seat. Well, that's kind of reflective of our degrees of freedom. Although n was 1, excuse me, n was 4 in this case, our degrees of freedom is n minus 1 or 4 minus 1 or 3. Degrees of freedom is quite often going to be 1 less than the number of items in your data set. So degrees of freedom is going to be n minus 1. Now, how does that affect our student t distribution? Our student t distribution is going to change with degrees of freedom. So if you click back to that Desmos link that I sent you and scroll around till you find n is the number of degrees of freedom, and start boosting that up. And what do you notice is happening as you increase the degrees of freedom?
It becomes more normal.
Yeah, becomes more and more like the normal. In fact, after a little while, it's pretty hard to distinguish between the two of them, isn't it? I mean, it just doesn't really look like there's much daylight between them at all. That's okay. In fact, that's exactly what happens, is that as the sample size increases, or your degrees of freedom increases, the t distribution looks more and more like a normal distribution. So let's write that down as well. As degrees of freedom increases, the t distribution looks more and more like the z distribution. And the z distribution is the standard normal distribution. So standard normal. Those two are interchangeable. And let's see that. Let's just see that for ourselves and get acquainted with finding values for the t distribution on statdisk. You can also find them on Google Sheets or on your graphing calculator, but I think it's going to be just absolutely most convenient to work with them on statdisk. All right, so open up statdisk, and then we'll go to the analysis menu, and then underneath there would be probability distributions. From there, you should see the student t distribution. So let me click over to there. So over to statdisk, then analysis, probability distributions, and then student t distribution. Should give you something like this. Now, what's a little bit annoying and or frustrating is that there's a little lack of consistency between what they do with the t distribution and what they do with the normal distribution. It's just, you're just going to have to pay a little bit of attention. Now, as I said, the student t distribution is something that changes with degrees of freedom. And I want to illustrate that this way. We're going to look at the student t distribution for degrees of freedom equal 3. Degrees of freedom equal 10. And degrees of freedom equal 20. I want to find the point on the student t distribution with 5% of the area in the right tail. So this is just a problem I'm making up here so that we can practice finding these things. So 5%, 5%, and 5%. Let's see how this changes. So we'll start with 3 degrees of freedom. And then I want 5% of the area to be in the right tail, so that the setup is really going to give me the answer to this one right here. 5% of the area in the right tail is going to happen when the t value is 2.353. So 2.353. Okay. Well, what happens if it was 10 degrees of freedom? Why don't you put in the chat what you get when you have 10 degrees of freedom, and then work on 20 degrees of freedom. Find those t values.
With the same area to the right?
Same area in the right tail. Mm-hmm.
Okay.
Okay, cool. Bunch of people there. Megan, Brooklyn, Ali, Nicole, Kelly, Don, thank you. All looking good. And Noelle, Megan, Brooklyn, Reagan, Katerina, Kelly, Don, Josh, all coming up with both of those values. So about 1.812 when you have 10 degrees of freedom. And then finally at 20 degrees of freedom, 1.725, we'll call it 7.725. So, okay. And it's progressively getting smaller. That's fine. Now we said that we can compare this to the normal distribution. When the degrees of freedom is pretty high, then this is looking more and more like a normal distribution. So let's find that value from the normal distribution. Now, as I said earlier, the normal distribution, the way they set that up works a little different than the t distribution. So if I go to the normal distribution, there's probability distributions, normal distribution. This time it's telling me the cumulative area from the left. So if I have 5% of the area in the right tail, how much is in the left tail?
0.95.
0.95. So when I put in that, then I get 1.644 for the z value. So the z value that these are all getting closer to is 1.645.
So is the z value basically from like the left and then the t would be the right?
Well, you can, it's just the way that these are set up is the way to find the z value given an area is you got to put in the area to the left. With the t values, you got to put in the area to the right. So it's a little inconsistent that way. It's not something I can do anything about because I didn't write the program. I wish it was a little bit different, but they're still getting at the same thing, which is the area in the right tail is going to be 5%. Now, what's happening is that as you increase the degrees of freedom, this number is getting closer and closer to this one. And you can experiment as much as you'd like. We'll go back to the student t distribution, and I'll put in higher and higher degrees of freedom to see how close I can get to 1.645. So let's put in degrees of freedom equal, say, 50. And I need to put in an area to the right of 5% again. So you're getting closer, 1.675 as opposed to 1.645. Go up to 100. You know, again, you're getting really, really close. You'll never actually get there because we can't go to infinity, but you can get as close as you like, I'm sure. Yeah, that's pretty close. That's really close. Okay, so finding the t-value is going to be one of the things we're going to have to do there. Are you comfortable with finding the t-values? In other instances, what's that? Doing good there? Thank you. So let me go back here. In other instances, you may have the t-value and be asked for the area. So if I had 10 degrees of freedom and a t-value of 2.013, then it gives me all kinds of things about the area. So area to the left of this would be 96.4%. Area to the right would be 3.5%, 3.6%. So there's a lot of different things you can look at in terms of the area, but you can use this table or this menu option in a couple different ways. Now, the way we need to use it is in creating confidence intervals. So let's see, let me look back here. That's where the t-distribution falls in terms of finding a confidence interval. You got to find t sub alpha over 2 times the degrees of freedom, or for the appropriate degrees of freedom times the standard deviation divided by the square root of n, sample size. That's going to be the point in the t-distribution with alpha over 2 of the area in the right tail. So t sub alpha over 2 is going to put alpha over 2 of the area in that right tail. That's for the appropriate degrees of freedom. Now, there is good news here for us, and that is statdisk is going to take care of an awful lot of this. So that's a good thing. Let's take a look at our handout and work a couple of example problems from there. There's going to be two basic kinds of problems that you're going to face in terms of finding confidence intervals. One in which you're given the summary statistics like you are here, and the other one in which you're given just the data. And we'll do examples of both of them. So for this first one, we have summary statistics for randomly selected weights of newborn girls. We've got 157 in our sample, 30.8 hectograms is the mean, the sample mean, with a standard deviation of 6.2 hectograms. Kind of strange to see that unit of hectograms. I did check it out earlier. It does translate to about 6.6 pounds. That'd be 30.8 hectograms. It's still kind of weird. I don't know. Okay, so let's write down some examples here for ourselves. Or excuse me, not some examples, but some data. This is example A. The items that we need to take care of right now are written in green or highlighted in green. 157. That's the number of samples. 30.8 is our sample mean, and our sample standard deviation is 6.2. There's also one other thing we need to take note of, and that is we want a 95% confidence level. So, okay, cool. 95% confidence level. Now, why do I need to take note of that? This tells me what alpha is. You might remember that alpha is 1 minus the confidence level. So what's alpha going to be?
0.05.
0.05. Yay. maybe we should practice calculating T sub alpha over 2 for this one. Yeah, tell you what, we'll hold off on that. There are some problems that we will look at that ask you to find that value. You know what? Yeah, let's actually find that value. So if n equals 157, anyone want to guess what the degrees of freedom would be here?
156.
Yeah, 156. Good. It's just one less than n. And to find t, our t sub alpha over 2, that's part of our error term. T sub alpha over 2, the appropriate degrees of freedom, s over the square root of n. We're going to need to find this for this value of alpha and the appropriate degrees of freedom. So t sub 0.05 over 2, 156 degrees of freedom, is going to be t sub 0.025 for 156 degrees of freedom. Let's look that up, figure out what that is. So we'll go back to statdisk for that. Change our degrees of freedom to 156. I'll get rid of this because what I want to put in is an area in the right tail. How much area should be in the right tail?
0.05.
Actually, that 0.05 got divided into 2 tails.
Oh, 0.025.
Yeah, there we go. Thank you. 0.025. So let's put that in here. 0.025. Yeah, no, I put it in the wrong spot. Area.
Wait, why did it become 0.025?
Because that probability gets divided by 2. The 0.05 gets divided by 2 as part of this little formula. So 0.05
Gotcha.
divided by 2 is 0.025. And be careful. You don't want to put that value in as your t value. We want to put that into this part right here. I want the area to the right of t to be 0.025, and then let statdisk figure out the t value. And it does. We get 1.975. If you put that together with the standard deviation and alpha, that should give you the error term. So if I take this and multiply it by the standard deviation divided by the square root of 157, not 156, but 157, that should give you my error term. Let's just do that real quick. I'll do it here. 1.975 times 6.2 divided by the square root of 157. So about 0.97 something. Okay, that's fine. We'll keep that there for the moment. Now, the goal, though, for us is to not really have to do too much work by hand. And in that respect, there's good news. So let's go back to analysis. This time, we're going to go down to confidence intervals. So click the analysis menu, then the confidence intervals submenu, and you've got 7 choices here. We can eliminate a lot of these choices, right? We're not trying to find a confidence interval for a population proportion. We're not trying to find a confidence interval for a standard deviation. So it has to be one of these: the mean 1 sample, mean 2 samples, mean matched pair. Well, we've only got 1 sample. So I'm liking that one. Here's our mean 1 sample. Confidence level is 0.95. Our sample size was 157. Our sample mean was 30.8. sample standard deviation was 6.2. And they ask you, do you know the population standard deviation? The answer is no. If we did, we wouldn't put in the sample standard deviation, we'd put in this instead. Are we okay with how we filled out our little menu here?
Yeah.
All right, so pretty much all of this stuff is given for us. Let's click the evaluate button. Well, one thing is kind of cool. We nailed it with our error term, right? Our error term was 0.977. Nailed it. So you should be able to take X bar plus E and X bar minus E and get exactly what we got, or get exactly what they've got right here, which is your confidence interval. So we've got 29.8 is less than mu is less than 31.8. Yay! There's your confidence interval. How's that one looking?
Good.
Good.
Now, technology is saving you an awful lot of work. So there is one thing that I'm going to ask in return, and that is, I want you to be able to state your conclusions in words. Words that somebody could read this and understand it, even if they haven't taken a statistics class. So
I have a quick question. When you
Yeah.
get the answer for confidence interval, do you just write it the way it is, where it's like the number and then mean and number, or is it just one number?
So there's a couple ways you can write this. One is like the interval like you have here. And for the mean, you're going to put this symbol, which is mu, because you're trying to estimate the population parameter. Now, you can take a sample that's a point estimate of your work, the point estimate of the population parameter. But you know that if you took a different sample, you get a different sample mean. There's variability in that. So to be a little bit more confident in this, you create a confidence interval and say, all right, the mean is probably in here someplace. We don't know where, but it's probably in here. You could write that different ways. You could write it as 30.8 plus or minus that E term, which is 0.977. So that's a different way you could write it in terms of your confidence interval. The nice thing about that is it shows you what your point estimate is when it says, okay, that's how much your error is. So you got an error that's a little bit less than 1 in width. So for that, did that cover your question?
Yeah, so basically it is a range, but you can write it in different ways
Yes.
as a range.
Yeah, and you should be able to go back and forth between either of these. If you had this one and you wanted this one, you could add these two together and divide by 2, that is average them. That would tell you what the midpoint is. And then once you have the midpoint, you could subtract either of these to get that distance. So,
Okay, and if it was like a problem if it was like a question problem, either answer would be fine, right? Or it wouldn't like tell us to change it?
it would probably tell you which form it wanted it in.
Oh, okay.
So that you won't have to wonder like, gee, do they want it like this or this? They'll tell you.
Okay.
All right, I appreciate the questions there. Thank you. Now, the last thing that I want to do here is write it in words, because eventually you're going to need to communicate your results to somebody who hasn't had the benefit of a stat class. So this is how I'd like you to write it, and it follows along exactly with what we did with population proportions. We can be 95% confident that the true population mean, or true population mean birth weight is between, where was it? 29.8 and 31.8 hectograms, which is the weirdest unit. When I get it, there's 10 hectograms of 1 kilogram, but it's just odd to see. Grams, kilograms, micrograms, I get. I've just never seen anyone use hectograms. How are we looking with that conclusion? Most of this is cookie cutter. You know, this stuff about we can be blank % confident that the true blank. So here's some things I want in all of your statements about your confidence interval. We can be blank % confident that the true, and then now you got to talk about what parameter you're dealing with. True population mean, birth weights. This part is going to change from problem to problem. Is between, you know, and then fill in numbers. What this avoids is talking about probabilities, because talking about probabilities here would be inaccurate at best. The only probabilities that are really involved are 0 and 1. We don't know which. This interval either contains the true population mean or it doesn't. We don't know which. So the probability, if you wanted to talk about probabilities here, would be 0 or 1. So do yourself a favor, talk about level of confidence. Level of confidence is the confidence in our procedure. 95 times out of 100, this procedure will result in a confidence interval that contains the population mean. Any follow-up on our conclusion here? Now there is kind of a part B here that we're going to look at. So let's do that. Says, are these results very different from the confidence interval 30.1 to 32.1 hectograms with only 18 sample values? Okay, so let me write that down. 30.1 to 32.1. So that's an alternate confidence interval. Are these confidence intervals very different? Well, let me put those all on a number line. There's 29.8. There's 30.1. There's 32.1. And, excuse me, I should do 31.8 first. Yeah, rats. I'm going to keep these in order. All right, little Photoshop there. 31.8 and 32.1. So we'll look at these confidence intervals. I'll look at this one. I'll put in blue. And this one I'll put in green. So we'll start with the first one, the one that we got. That said that, you know what, we're not sure where the population mean is, that is that parameter. But we're pretty sure it's somewhere here. That's where we think it is. And the second confidence interval, the one that comes from the book, says, you know what, we think it's somewhere between here. The question is, are these confidence intervals very different? And the answer is no, because they overlap. And what that means is that mu, the true value that we're trying to estimate, could be somewhere in here. We just don't know where. But that would make both confidence intervals true. Both confidence intervals would contain the true population parameter, even though they weren't exactly the same confidence interval. So are these very different? The answer is no. Are the intervals very different? No. And that's because they overlap.
So it ignores the fact that the numbers are only different by about 0.3 hectograms on each side.
Yeah.
Because it overlaps, it doesn't matter how far the numbers were, but if it overlaps, it's
Yeah,
true. I mean, they're not
exactly. So,
different.
now, I can't be 100% certain, but I'm pretty sure that what the author's intention is to draw your attention to the fact that the intervals overlap. And because they overlap, they're not that different, as opposed to, so alternatively, what if I had something that looked like, give me a second here. Here, I had, say, 28.1 to 30.1 and 30.3 to 32.1. If I had intervals like this, so I had this one here and this one here, then those would be very different. There's no way that both of these could be correct. At most, one of them is correct, right? So this would be something that'd be very different in terms of the author's mind, and mine for that matter, because they don't overlap. They can't both be true at the same time. So that's the big point here, I think.
Gotcha.
All right. Appreciate the question. Thank you so much. Anything else on that one? Now, one of the things that I've kind of glossed over a little bit, I am going to go back and change that, is the fact that in creating this confidence interval, you actually have a couple choices as to how you do it. Now, the fact that you have a couple choices is kind of in theory. In practice, I really think you only have one choice. And so let's look at this bit about T or Z. When you create a confidence interval for a population mean, you've got really three choices. One of them results in a T value, one results in a Z value, and if neither of those is appropriate, then you're going to have to use some non-parametric methods discussed at the end of this book. There's also some bootstrapping methods, but that's not part of this course. So, what are the conditions under which you use a T distribution? Well, the big one to use a T distribution is that you don't know what the population standard deviation is. That is, sigma is not known. Okay, if sigma is not known, then in order to use a T distribution, you have to have one of two things. You have to have a normal population, or the sample size is greater than 30. What if you do know sigma? If you do know sigma, then your confidence interval is going to be based off of a normal distribution. So if that's the case, you know sigma, and you can assume that the data is normally distributed, then you're going to use a Z. Or if you know sigma and your sample size is greater than 30, again, you're going to use a Z. So a couple circumstances there. Now the author puts a helpful little note down here that let me highlight. In reality, sigma is rarely known. And if you think about it, it'd be really odd that somehow we don't know what the population mean is, that is mu. That's a horrible mu, I'm sorry. We don't know what the population mean is, but somehow we know what the population standard deviation is. I just don't see how that's going to happen very often in practice. So in practice for us, in this class, for the most part, you're going to be using a T distribution right here. Okay. Let's practice another confidence interval. We'll come back and practice a few problems like this, the t distribution versus the z distribution, or none of the above. But for now, I want to practice a little bit more with the t distribution. Let's move on to example B. Example B. A data set includes 107 body temperatures of healthy adults having a mean of 98.7, a standard deviation of 0.72. Construct a 99% confidence interval estimate of the mean body temperature of all healthy humans. All right, let me just stop right there. We're actually going to do this a little differently than is intended here from the problem, because I want to give you a chance to play with some data. And the cool thing about statdisk is that it's got data programmed in from the book. So let's open up statdisk. This time we're going to go to data sets. You want to choose 13th edition and carefully scroll over to body temperatures. So data sets, 13th edition, then body temperatures. Okay. So let's see here. There's your data set. And I think they wanted a 99% confidence interval. So we'll put 0.99 here. Actually, you know what? I screwed up a little bit. Before I start with all that stuff, we're not going to be using summary statistics like we did with the last problem. In this problem, we're going to use the data. So start by clicking Use Data. And now I'll change this to a 99% confidence interval. We get to select which column of data we're going to use. So I'll give you a choice. Day 1 at 8 a.m. or day 2 at 8 a.m.
2.
2 it is, thank you. So we'll do day 2 at 8 a.m. Now we don't know what the population standard deviation is, so we'll leave that one alone. Just say, okay, I don't know what it is, we'll leave it there. And when you click, it does everything for you. It's wonderful. It gives you E, it gives you the population, or it gives you the confidence interval, etc. So let's just write down a couple important things here. This is for example B. So we get the margin of error is 0.22. So that means the margin of error is 0.22 degrees. And our confidence interval is going to range from 97.3 degrees is less than mu is less than 97.7 degrees. I imagine that as of late, you probably have gotten your temperature checked much more often than you're used to. Myself included, just got mine checked yesterday. It's 97.1, so a little bit on the low side there, but that's okay. There is one annoying thing that's missing out of this, and we can get it a couple different ways. But the one thing that's missing that I don't like about this is it doesn't tell me what the actual mean is. It is, all right, well, what's X bar for this data? And for that matter, what's S? Well, they don't tell us. As far as the mean is concerned, you can get that just by averaging those two pieces of data. So if I take 97.3 plus 97.7 and divide it by 2, or add them up and divide by 2, I get 97.35. So that's X bar. But there's actually an easier way to do it than just that. Nonetheless, you should be able to find that if you need it.
I think you missed the 0.3.
You're right.
Like on the calculator.
You're right. I did miss the 0.3. Good eye. Just a quick FYI, if you're doing something on a calculator and you need to edit things, you can hit the second button, then the delete key to insert a value. So there's my 0.3. So 97.5. Yeah, that makes more sense. So X bar 97.5. I'm going to leave that blank because I'm going to go fill that in from someplace else. Why don't you take a second, see if you can't formulate your conclusion in words. So you should end up with something that looks like this. We can be 99% confident that the true mean body temperature is between 97.3 and 97.7 degrees Fahrenheit. Yay. Now let's take a look at the rest of the problem. Are we okay with our conclusion here?
Yes.
All right. Thank you. Let's look back at the problem. It says, what does the sample suggest about the use of 98.6 as the mean body temperature? So, okay, 98.6. Well, let's draw this out like we did just a bit ago. We've got our confidence interval. That was 97.3 to 97.7. And then over here we have 98.6. So here's our confidence interval. What's that saying about 98.6?
A bit high.
Yeah, it's a bit high. Yeah. This is a really old value. Have I talked about that to you guys? Where this number came from? All right, let me just mention a quick word about that then. It comes from an old German study. It's 150 years old. And this German physician analyzed like 1 million temperatures from 25,000 people. I mean, wow. It's just a crazy amount of data to have to collect and analyze by hand. So A+ on perseverance there, but 98.6 sounds pretty precise, right? I mean, 98.6, you got that 0.6, but that 0.6 is really an artifact. His average body temperature was 37. How can you make sense of it? How is it 37? Can anyone figure out why? He was working in degrees Celsius. And so to convert it to degrees Fahrenheit, you have to multiply by 9/5 and add 32. And that's how you get your 98.6. So that 0.6 is really kind of artificial. It just comes about by converting degrees Celsius to degrees Fahrenheit. So, yeah. So not only is there a difference in body temperature between day and night, but there's also a difference in body temperature between men and women. So this 98.6 just really isn't that good, but it's enduring. I mean, that's the number I grew up with. Oh, average human body temperature, 98.6. So, okay. One last thing to comment on that. I mentioned just a moment ago that, you know what, we're going to leave this blank for the minute. And I'm going to show you how to get those values, because weirdly enough, they weren't included in the output here, right? I mean, we got what E is, we've got what the confidence interval is, but they don't tell us what S is, they don't tell us what the mean is, nothing. So go back to statdisk, click data, and then go down to explore data / descriptive statistics. When you click that, you'll get a little drop-down menu here. Let's select our data from day 2 at 8 a.m. When you click evaluate, you get more statistics, more numbers than you'll know what to do with. You got your mean, mid-range, median, root mean square, variance, standard deviation, all the different quartiles. Over here, you've got a distribution, nice histogram, box plot, and a normal quantile plot. Let's start by looking at the histogram. Does this look like it's normally distributed? Does that look like it comes from a normal distribution?
No.
No, not so much. And we look down here at the normal quantile plot, yeah, it's kind of hard to tell, but I mean, it doesn't look as bad here as it does up here in the histogram. So this leaves a little room for subjectivity, but in my mind, especially based on this, it's not a normal distribution. But all the numbers that you might need or want, like the mean, 97.49, and the standard deviation was 0.700, 0.701, etc. You can get tons of that information from this Explore data column.
So I have a question. Just
Yes.
by looking like for like at example B, how are we supposed to know to kind of like how to go about solving this problem just by like, if I were to look at example B, I would not guess to like go into data sets and do all of this. Like, I don't know how, you know, I don't know how to go about it.
So the big clue is that you're asked to construct a 99% confidence interval. And it's cut off a little bit on my sheet here. Let me see. Yeah, there we go. Construct a 99% confidence interval. That's your clue. And it's a constructing a 99% confidence interval for the average or the mean body temperature. So there's your big clue right there. Construct a 99% confidence level. And when you go to statdisk, pretty much most of what you're going to be doing is going to be going to the analysis menu. When you scroll down there, you see confidence intervals, and then you just have to choose the right one. All right, you're dealing with a confidence interval for a population mean. Okay. And later on, we'll do some other confidence intervals as well. In section 9 or 7.3, we'll start dealing with a confidence interval for standard deviations. So it's going to depend on what the question's asking, but you're going to find what you need right in here, especially if it's a confidence interval. Does that help out a little bit?
Yeah, thank you.
All right, thank you. Any other comments or questions about example B here? All right. Now, one of the things that we have to look at yet is how we're going to choose between a Z distribution and a T distribution to create our confidence intervals, but we'll do that after a quick break. So we'll stop things here.